Okay, good afternoon, everyone. My name is Vinod, and I'll be talking about some machine learning work that's happening at Microsoft applied to the problem of service health monitoring. So I'm sure most people here are already familiar with the problem of service health monitoring, and I just want to recap, the main motivation behind this problem. So companies that run cloud services obviously don't want customers to be impacted by whatever outages that are happening in the data center, in the service. So it's crucial that issues are detected as early as possible such that the engineers can fix the issue and customers won't notice anything. Otherwise, you will get embarrassing outages, financial penalties for missing SLAs, and so forth. So the financial incentive for working on this problem is very clear. In this work, our goal is to apply machine learning methods on the telemetry that's logged by these services in order to build detection systems that can accurately detect issues as well as diagnose the root cause. And of course, this is a very hard problem, as many of you would already know, and there are all kinds of standard challenges that we keep seeing in the papers, things like we need to be able to do detection in real time, it has to produce interpretable results, and so forth. But apart from all those standard challenges, I just want to draw your attention to a couple of other things. So the previous talk was great for setting up this. One of the things that we notice in our application is that it's very difficult to detect issues by just using individual variables. Suppose you have these KPIs or performance counters, right? Any one of them by itself may not be a very good indicator of an issue. Instead, we need to combine information across multiple variables in order to reliably detect issues, right? So how do you solve that problem, the multivariate problem? Another issue is domain knowledge. So for most of these services, we have very detailed knowledge about how the architecture of the service, which hopefully we should be able to use as part of building our detection system, especially because we don't have a lot of labeled examples. In the absence of labels, it makes sense to plug in as much domain knowledge you have about how the service is architected in terms of components, subcomponents, the entire hierarchical design of that service, bake that into the detector, right? So these are some of the challenges that we're going to look at in our particular work. And just to give you a preview of what we ended up doing, essentially we ended up defining a learning algorithm that learns a hierarchical detection system from data, unsupervised. It'll become clear later what we mean by that. And the learning approach that we're going to propose, it's scalable because the particular application we are looking at actually involves dealing with a very large amount of telemetry data, potentially thousands of counters. And we have already deployed this. It's running in production for 3 months now, where we are monitoring the internal big data platform inside Microsoft. So this is a very large service, probably one of the largest big data platforms in the world, consisting of several tens of thousands of machines. And we are analyzing the telemetry data coming from that service to detect and diagnose issues affecting it. So before I go into the details of the algorithm, let me start with a simple example just to give you an intuitive sense of what is the challenge that we're trying to solve. So I mentioned about there being a lot of telemetry data available. For now, let's focus just on performance counters. So these are time series, KPIs. You can imagine these are things like latencies, how many API calls are coming into the service, how many failures are happening among those API calls. Imagine all kinds of variables getting logged at regular time intervals, let's say once every minute. And that gives you a very high-dimensional time series. And now the goal is, can you use that time series to detect issues, right? So right off the bat, one of the first challenges that we had to face in our application is that for any given issue we are looking at, actually only a very small subset of this data is directly indicative of the problem, right? So out of the 1,000 counters, maybe only 6 of these counters are actually indicative, right? So I've plotted here 6 different counters where x-axis is time and y-axis is the value of the counter. The the meaning of the counters doesn't matter. But what you notice is that, so that red interval in the middle indicates an issue that affected the service. And you can see here that there is a pattern that indicates this particular issue, which is that the counters on the left are spiking very high during the issue time, and the counters on the right are all showing a dip. And together, the combination of these two patterns actually indicate that there's an issue happening. Whereas if you were to set up a handwritten rule on any one of these counters individually, you're very likely to get a lot of false positives, because maybe in any one of these counters, the spikes are fairly common, right? But when they occur together, they have a very different meaning. And how do you discover such combinations automatically? That is the main challenge we are looking at. Now, this might be the case for a particular issue type, which I call here issue type 1. But there might be other issue types where possibly the same set of counters are involved, but maybe the pattern that you see, the combination of patterns, might be different. So for example, maybe only the blue counters spike, and the green counters may not show anything unusual for this particular type, right? So that means out of all the counters we have, first of all, we need to figure out that, hey, only this very small subset is involved. Within that subset, we need to identify, hey, we can group some of these counters by the patterns they show, and then actually figure out what are the patterns that we need to see in each of these groups. So I hope the problem setup is clear. Now, of course, time series anomaly detection is a vast area with lots of papers. I'm not going to cover all of those papers. Even multivariate anomaly detection, there's tons of work. One thing I just want to point out in terms of multivariate anomaly detection is that I'll explain the algorithm later, but in some sense, we can actually plug in many of these algorithms in the literature into the framework that we're proposing. So we're sort of trying to build something higher level rather than just propose yet another anomaly detection algorithm. And of course, service health monitoring is also a well-covered topic in the literature. Now, one very interesting subtopic within the literature that's directly relevant to our work is this subspace anomaly detection. So as I'll explain later, we will end up using something called a Gaussian graphical model in order to automatically identify the subset of variables that are involved in an issue. The reason we went with that approach is because it scales very well. It has very nice properties, theoretically, that say that it scales very well to high-dimensional data, even with the limited number of samples. But there are alternative methods. For example, this approach, high CS, is a very interesting method. This is another alternative that we are interested in trying out, but for now, we went with this Gaussian graphical model approach. Okay, so let me quickly summarize the main ideas, and I'll walk you through the main steps of the algorithm. So what we are trying to build is a hierarchy of detectors, right? For the purposes of this talk, just think of a detector as a function that will take some input time series, and it'll compute some output score that says how unusual does that time series look. So high score means very unusual, and low score means perfectly normal. Now, at the lowest level of this hierarchy, we have detectors running directly on the raw telemetry data, for example, performance counters, KPIs, and so forth. And at the higher levels, we have detectors that are running on top of the lower level detectors. That is, they combine the outputs of the lower level detectors to define higher level ones. And you can imagine a full hierarchy of that form. Now, how do we learn this? Our learning algorithm basically consists of two main steps, which I've called here as grouping and combining. Think of these as sort of two subroutines that we repeatedly call inside our algorithm to build each level of our hierarchy. So as I mentioned before, at the lowest level, we have the telemetry data. And we have a first level of low-level detectors that we apply here. Now, like what we saw in the previous talk, this first level of detection could be any of the off-the-shelf standard algorithms that's in the literature. Things like detecting shifts in mean, detecting spikes, or, for example, some density-based approaches like kernel density estimates. All of these are actually things, many of the things that are listed in the previous talk, we are also applying. But the thing is, here is where the engineers have the most intuition about what is worth detecting. If you talk to the engineers who run the services, they actually can tell you, hey, yeah, if that counter shows a spike, I know something is going wrong, right? So there's quite a bit of intuition about what should be detected in individual counters. What the engineers don't know much about is what specific combination actually indicates that, hey, this particular issue type is happening. And that's the part we are trying to solve with machine learning, right? The other interesting thing here is that, of course, experts write rules based on individual counters, like threshold-based rules. And we can also plug in those detectors at the lowest level as well. So there's no expectation that the lowest level detectors are very reliable. By adding more layers on top of this, the hope is to improve the quality of the detectors, make them less noisy, reduce their false positive rate, and so forth. So to build each level of the hierarchy, we alternate between grouping and combining. And in the grouping step, what we do is we identify a group of related detectors in the current level. And in the combining step, for each of the groups that were discovered, we ask, how do we combine the scores of those detectors to define the score for the next level detector in the hierarchy? So imagine applying this in several levels to build up the hierarchy. Now, I mentioned this issue of how do we make use of domain knowledge about the service, right? If you know that your service consists of two different components, which I call here component A and component B, we can actually apply this algorithm independently on each of these components. And then if you're interested in detecting cross-component issues, now you can start applying the learning algorithm across components, right? The detectors that were learned across, in different components. So this way, the idea is that you build up several layers, and at the very highest level, you have detectors that have visibility across the entire service. And presumably, that'll allow the highest level detectors to produce very much more reliable alerts than the lowest level ones. So I'll show some results regarding that. Let me just quickly explain how the grouping and the combining is done. So for group discovery, we are trying to find out related detectors. And we apply this algorithm called a Gaussian graphical model, which basically learns an undirected graph over a set of variables with the constraint that there should be very few edges within the graph. And what I've shown here is, so once that graph is learned, we can do clustering on the edges to identify densely connected subgraphs. And those densely connected subgraphs are the detector groups that we end up using in our algorithm. So I've shown here some of the steps that are involved. I'll skip the details. They're in the paper. But here we ended up discovering 6 different groups in a particular level in our hierarchy. So the clustering step is done using an algorithm called affinity propagation, which has the nice property that you don't need to specify the number of clusters ahead of time. And for combining, that is, once we identify a group of detectors, we just use a simple average to compute the group score. And this has the nice property, again, that since averaging is linear, things remain very interpretable. And you can actually start at the highest level of the hierarchy and trace your way down to the lowest level counters to figure out, hey, who should I attribute this alert to, right? Which counters at the lowest level are responsible for the alert that I'm seeing at the highest level. So as I mentioned before, we deployed this in production. And our production system basically consists of 2 different pipelines. One is the training pipeline, which is shown at the top, which takes several months of historical data in order to learn this hierarchical detector. So that training is done offline in a batch mode. And once the detector is trained, we plug it into the near real-time pipeline that is used to detect issues in the latest counter data. And when the detector fires an alert, it's sent out as either an email or as some kind of visualization in one of the tools that we have built. So we have a separate line of work on how do you visualize anomalies and so forth, on which we will be writing some papers as well. Okay, so let me just walk you through a sample example of what happens when we apply our detector. Imagine that at the raw level, at the bottom, we have 75 different counters coming in as a time series, and we apply some low-level detectors, things like mean shift or spike detection and so forth, on those 75 counters, and the score time series generated by those low-level detectors are shown on the left side, right? And you can see that they're all overlaid on each other, and it looks like a complete mess. But then we start applying our algorithm, and the first step is the algorithm discovers 5 different groups out of those 75 detectors. So I've shown those 5 groups there. Now, what you see as a vertical band on that plot is the time interval for a specific issue. And what we want to see is a detector that gives you a very high score during that interval and low scores elsewhere. And you can see that at the first level, it's simply not happening. Now, after grouping, we combine the members of each group into a single, second-level detector. And if you look at the score time series of those second-level detectors, they look more promising now. The noise has come down. You can start to see some spikes during the issue interval. But there are still some noisy patches elsewhere, so it's still not perfect. Apply our algorithm again one more round on top of these 5 second-level detectors to come up with a third-level detector. And now you can see that at the highest level, the detector is giving us the desired behavior. Now, once an alert, suppose we set a threshold here as 0.5, and an alert gets thrown, the engineer who is at the receiving end of that email, he doesn't have to be completely lost as to why that alert was thrown. He can actually step his way through this hierarchy and figure out, hey, this subset of counters contributed the most to this particular alert, and that gives me an initial clue as to how to fix this problem. So interpretability is a nice built-in feature of our approach. Here's a slightly larger scale evaluation where we took some 19 issues that happened recently in our service, and we again asked what is the performance we get at each level of our hierarchy. And the same message is shown here in a slightly more quantitative way, where green is the highest level, red is mid, and blue is the lowest level. And you can see that, let's say you fix your alerting budget to be some 100 alerts over 6 months. The highest level gives you the highest fraction of issues detected for that particular alert budget, right? So you see the benefit of building multiple levels in our detector. So there are a couple of directions of future work we are looking at. One is the Gaussian graphical model that we used in our work is making a Gaussian assumption about the data, which is not true. And as the previous talk also mentioned, many of the counters are actually very heavy-tailed, Pareto distributed, and one of the directions we are looking at is how do you adapt the Gaussian graphical model to be applicable to non-Gaussian data. And the second direction we are looking at, now that our system is in production and emails are going out and engineers are looking at our emails, they're giving us feedback now, saying, hey, this alert was a false positive, it should not have come, right? Or yes, this was a good alert and it indicated an issue. Now, how do we make use of those labels in order to improve our hierarchy? So we're looking at how to do that. Thanks.
Thank you. One way at the back. We need a routing algorithm for the question so our volunteer doesn't have to keep running around all the time.
You mentioned the budget of a fixed number of alerts per month, but typically the kind of budget you want is a trade-off between catching all the alerts versus false positives of triggering too many alerts.
Right.
So can you, in your application, walk us through that trade-off?
Yeah. Typically what happens in practice is that there are enough sort of humans available to investigate all the genuine issues. The key problem is there is a budget on how many false positives you can hit them with. So that sets an upper limit. But I mean, if there are sort of 200 issues happening in 6 months and your budget is only 100, obviously people will investigate all the 200 genuine issues, right? But typically the number of genuine issues is not very high.
Does that, can you take that into account into your algorithm? So, because this is a business decision which is probably known a priori, right? Staffing levels and availability of people to fix these issues.
Right.
Can you take those into account?
So that comes into play when we set the thresholds. And in fact, we have different levels of severity for alerts. And if we know how much manpower is there, we can afford to be somewhat loose on the thresholds and let more alerts come, right? So it comes into play in how we set the thresholds, how conservative. Yeah.
So continuing the previous question, basically what your precision looks like.
So this particular plot we are showing here, precision is very hard to measure in our application.
Why?
Yeah, so I'll get to that. So we know certain confirmed issues. And we know that there are certain issues that are just unlabeled in the data. Okay, they simply went undetected. If a detector says, "Hey, there is an issue there," we should not penalize it for detecting that. It was just that it was a hidden issue, which nobody bothered to look at.
So, what does your precision look like on the issues that you do?
Right. So, to do large scale, asking engineers to look at, like, let's say 100 alerts to evaluate this is very expensive. Like, they would not be willing to do that. So because of that, we don't have a specific precision number. That's why instead what we have is, out of the known issues, what fraction did we detect, and how many alerts did we have to throw in order to detect that fraction? See, if we had sort of ideal, altruistic engineers in our team, they will be willing to sit through as many alerts as we throw and patiently say, yes, this was good, no, this was crap. I'm sorry? It's very hard to relate such low-level logs to high-level issues, right? I mean, failures are happening all the time, but they're not all issues, right? So the reason why we don't have a precision recall curve here is simply a manpower thing. We cannot ask people to label through all our outputs and tell us. But we have sort of done, a proxy to that here, which is imperfect, but yes.
Another question here.
So would it make sense to allow the domain experts to kind of participate in setting thresholds that might be different by sensor or different by kind of subject? They might understand the processes much better. And so if you have 6 categories, kind of like an equalizer, dial down this, I'm getting too much noise.
Yes.
Dial up this one, I'm much more concerned because it's got a higher profit loss.
Yes, so that's a very good point. Actually, that is one thing we definitely want to do, which is we want to bring in the expert into the loop. So far, we have not been doing that in a very detailed manner. But then as soon as you bring in the experts, you have to make it sort of simple and easy for them to do these things, and it should not require understanding machine learning algorithms running inside and so forth. So that part is also a bit tricky. So
Stereo equalizer.
yes, that's one possibility, yes.
So one more question.
Yeah. So you mentioned explanation. So could you extend this towards root cause analysis?
Yes, so the idea is that we want to use these kinds of explanations as a starting point. There's actually a separate tool that is dedicated just for root cause analysis. And our next step is to actually link this detection algorithm to that root cause analysis tool, such that right from the alert email, the user enters that root cause analysis tool, and the tool already knows that this is the subset of counters that's suspected to be involved in an issue, right? So at least he has a starting point for his investigation.
It's very nice work. Thank you.
Thanks.